First, let me thanks Dr. Reddy's give me these opportunities. I know him 17 years ago. So he is a kind of pioneer in the geoenvironmental engineering in US and in the world. And he do a lot of research, and he kind of give me a lot of good role model in terms of geoenvironmental engineering, especially in the earlier career. So I really appreciate these opportunities, and I hope I can keep moving forward for the geoenvironmental engineering. So this is today my presentation is an environmental investigation of the bio-modification of steel slag and coal ash through the uranium-produced bacteria and MICP. So this work is based on the two paper, and I go to present the two paper later. And today I'm focused on the two recycled materials, steel slag and coal ash. The steel slag is one of the byproducts from steel manufacturer. Is produce a lot of the steel slag. Most of them go to the landfill, but some of the steel slag can be used for recycle. For example, aggregate materials in constructions or granular based. But they have some concern. Sometimes they say, oh, they may have some environmental issue. So that's the way we need, as geoenvironmental engineer, we need to address that issue, whether this is a really toxical or is non-hazardous material. So we need to figure out what to do for that. So the ash, especially the fly ash, this is a big, always has kind of discussions, especially US EPA very carefully try to classify the fly ash, but actually in the currently up to the last year, they are almost 50 or 60% fly ash can be recycling. So they can be using for concrete products. They can use in roadways, constructions, embankments. So there are a lot of things to using, but sometimes when they're using is exposed to the strong environment. So people may concern about that, especially the newspaper or the they may say, oh, this fly ash is hazardous material. So that's kind of the make the reuse of fly ash is difficult to promote, because once it is classified as hazardous material, that will be big concern. So whether yes or no, so we need to look there what kind of environmental concern, especially the metal leaching. So this is the work we try to address from this research. And actually in the literature there, I just show some typical example. There is the research talk about what kind of metal leaching out from steel slag or the coal ash. So is the table show some kind of the elements they select, and the reason why they put this one. So is US EPA or the drinking water standards, so they put the environmental regulation there. They say no matter where the source coming from, they will check, make sure this you want to reuse steel slag, you want to reuse fly ash, make sure they generate the leaching less than these regulations. Otherwise, it will be classified as the contaminants. So that way is we really need to study that. But actually, when the people doing literature review, you find out there's a lot of work already been done, especially doing the reuse fly ash and the steel slags. People has two ways to do. One is focus on mechanical part. So is figure out how to study the mechanical improvements. And another thing they are looking for is what kind of environmental leaching of that. So many research, including the Professor Reddy's group and other research group, they have a publication about that. And they're using traditional way try to stabilize that or to reducing the leaching. But today I want to using another way, is biological way to try is that. It's called microbial-induced calcium precipitation. Some of you may be familiar with that one, we call MICP. The reason is that this bacteria has one thing very unique is this bacteria is currently there is can hydrolyze urine, and then when they hydrolyze the urines, they release carbonate ion into the solutions, and if the solution has calcium ions, so the calcium ion can be coming from you adding calcium ion in the solution, or you coming from, for example, the flash. You have some flash may have a higher calcium component in there, and maybe help them the solution to precipitate calcium carbonate. So here it is. The cartoon show you is here is how the bacteria looks like. The bacteria is long shapes. So the surrounding that is can be is negative surface charge. So they can attracting the calcium ion surrounding that. But when the uranium was hydrated by this bacteria, it will release carbonate ions. It's also to change the pH environment. It's favored to the alkalinity conditions, so the pH higher, about like close 9 or 10. So that favors the precipitations. So we can see here is when they precipitate, they're surrounding the bacteria. So the bacteria can serve as the core of these minerals. So the minerals, the calcium carbonates can be formed, and eventually they will surrounding the bacteria and will be cover the bacteria. So the bacteria kind of like will be die eventually, will be covered by the calcium carbonate. But once this new material form, they can bonding surrounding particle together. Currently, most of research we are using sandy material. The reason is this bacteria about like 2 micrometer longer. So it's difficult for the bacteria to go through clay soil. But for the silty soil or the sandy soil is easily go through. So that's the people using that. And when they're using that, a lot of time they are focused on is mechanical improvements. For example, you can do is change the soil properties. You can change the strength, and especially people want to using for the reducing the liquefactions, and even there go forward to the field testing, not just the laboratory studies. Another type of study using is concrete. So they are using self-sealing concrete. In last November, the first international MICP conference was hosting. So that's just a lot of current research going there. So that way is people try to using that, and when they're using, most of the time they focus on the mechanically. And another example is showing the brake. They call bio brake. So that's to make the brakes become it's a moderately strong like rock. So this is good. That make the materials good. So that's one type of work. But another type of work we want to think about that since the bacteria there. So I'm thinking about can we using that to study how to modify the coal ash, flash, and the steel slag to see whether their mechanical strength can be improved, and also can look what environmental leaching can be modified this leaching behavior. So that's the work we tried to do about like 2 years ago, and we start doing this work, and we have from literature we found out there's several other leaching reduction methods, but we say let's find another way using this MICP biological method to do that. And even the literature is limited on that research, so we say this objective try to study the leaching behaviors of the metal from the steel slag treated by MICP, and we also want to study the bacteria, how to modify this flash to evaluate the effect on the metal leachings. So that's kind of two objectives. What we did is, first thing, we use bacteria. Since we are a geotechnical engineer, so we really need help from the microbiology people to identify what kind of bacteria. So one type of bacteria, a lot of reference using is Spirosaccharidis. So this is kind of like most people using that, but again, there in the literature there are other kind of bacteria. So let's also open the door for the future research. We can try different type of research bacteria. This bacteria is when they start growing, they go through the traditional lag phase, log phase, stationary phase. So we really want to use this bacteria when they be kind of like before their stationary phase, they're really active conditions. Because bacteria try to keep growing, and so we want to make sure that's the best conditions. So we give them the cultural media, let them to grow, and we make sure they reach the 10 millions in terms of the number of bacteria. So when that solution is ready, so we put that, we make sure that the solution is ready. Now the next step is we go back our traditional geotechnical materials. So first thing we using steel slag. This steel slag is from the one of local industry steel plant. So the particle size can be arranged a lot, but we try to focus on between the US sieve number 10 to number 40. So that way we want to control the size of the steel slag. So that's we choose the part 1, part 2. Basically, we make 2 groups of the steel slag, the same source, but just 2 different size, smaller size, a little bit bigger size. And we also use EDX to see what kind of chemical composition in the steel slag. And you can see here the calcium oxide is almost 41% by weight. And also the XRD also showed this is what the chemical composition in the steel slag, and the pH of this steel slag is 10, about 10.1. So this is the material here. And since we want to study whether the how they are leaching, so we are mixing different kind of sand. So the sand is a local sand. So we're just using the local sand, mixing different ratio of the sand and steel slag. And the reason is we want to look the 2 parts. One is their mechanical way, how they are changed. Another way, we want to look what environmental leaching impact on the different steel slag percentage. So with that, and we move to the next material is coal ash. Coal ash is, we have, according to the ASTM standard, there are class C and class F and off specification. So currently we got 3 types of flash, and there one is type F. Basically type F is the calcium oxygen is about like 10%. It's low. So it's difficult using for self-cementations. You have to add in additional calcium solution to make cementation purpose. And but another 2 flash is off specification. So basically, it's not exactly class C or class F. That kind of a little bit off. And the pH, we also measure the pH of this flash about like 10 to 12. So this is the flash. Now we have steel slag, we have flash. So we also can look using the XRD and SEM to look basically we just character the materials. So look the flashed. So the flashed, you can, if you look the SEM, you can see this is a lot of void space. Basically, this void space we'll be using, we need that kind of void space The reason is we mentioned about this bacteria is about like 2 micrometer longer. So when the bacteria mixing, the solution mixing with flash, this bacteria need a little bit space to go through, to mixing well, or go through this coash. So that's just kind of enough void space in this coash for this testing. And now the procedure, how we do that. First thing is for the cementation testing. Cementation, the purpose is what is original, we have sandy soil. So you can see sand and we're mixing with the steel slag. So this is mixer of powder shapes and it's difficult to stand alone. So we have put a special a chamber to holding the samples to make the shape, because later we want to do unconfined compressor testing, triaxial testing. We need to make sure the cylinder shape. So before we do that, we have to make the bacteria. The first step, we cultivate the bacteria, we make the bacteria grow, make sure reach 10 millions in terms of the number of bacteria in the solution. Then we're mixing the bacteria with the sand and the steel slag. So once we're mixing that, then we put in this, this is, let me see here, this, you can see, this is individually is using geotextile. This geotextile is permeable to water, but is block the soil move out. So it can, basically this geotextile is fully permeable, also maintain the shape. So that is good to maintain the soil in terms of cylinder shape. So when we put a reaction kind of we call tank, this tank is we put the cementitious media, and we put cementitious media and we put X air because this bacteria need oxygen. So when reaction happens, there will be the bacteria will be start to dissolve the urine in here. So inside this tank, the urine will be dissolved by the bacteria, and so once they mixing that, so the calcium ions, so for this case, we add calcium ions. So calcium ion in a solution will react with the carbonates. But right now is all the carbonates will be surrounding the sand particles, will penetrate through to this geotextile, and then the calcium carbonate can precipitate between the sand particle. See, the original this loose materials, but once you have this precipitate calcium carbonate, they can bonding sand particle together after 7 days. But for this reaction, I just react for 7 days. You can keep going for 28 days. But the first 3 days, actually, the bacteria are really active. But after that, the bacteria was covered by this calcium carbonate, so their activity going down. And after 7 days, we stop the air pump. We take the sample out. We cut this geotextile. This one we can cut with scissors and throw away. So the sample will be look like a cylinder shape. That's depending what testing you want to do. You want to do unconfined compression testing, you can keep this cylinder shape. But if you want to do direct shear testing, you have to use in different size to do that. So it can be decide what size to using. But since we are using this method, we call immersive method. So basically immerse into the cementitious media. The literature also show you someone using injection method. So they keep pumping in the bacteria, keep pumping in and pumping out. So this is another way to do this MICP. So for this immersive methods, we the biggest sample size we can run up to the depending what the solution you have. So we keep this less than 4-inch diameters. So if you say I want to make a big sample, so you have to use probably injection methods. And so that's the first one. The second method I'm using is for the bio-modification, but this time for flash. But for this study, I will only including flash and bacteria and urea, no sun. So no sun involved here. And the reason is we want to look, we even don't adding calcium chloride solution in there, because the flash has calcium inside, so we can using that calcium ion to see how to modify these leaching behaviors. So this is the procedure here is once we're adding the bacteria in the flash, and then we're adding urea solutions. So we rotate that, and then we give air, because the bacteria still need air. So we measure the pH, we harvest it's several different days. Then we also oven dry the mixture, and we're using the SPLP to do the leaching testing for this one, for flash. So for the steel slag, we're using the EPA standards leaching test methods. For example, we use acid digester testing, try to basically it's kind of it measure all kind of metal in the steel slag. And we also use TCLP. TCLP is identify whether this material is hazard or non-hazard. So this is the using the, you can see extraction fluid, the pH is 2.88. And another one we're using SPLP. So this one is to testing whether it's beneficial reuse or not. So the extraction fluid pH is 4.2. Then the next one is just water leaching testing. So with this leaching testing, and we have the solution, we want to measurement how what kind of heavy metal in there. So we use MICP, and so this is the equipment we have, and this is the detection limit. Again, this is some metals we can measure. So I'm just using the mark to highlight what kind of heavy metal we go to measures. And it's meantime, we also can using XRD to measure the minerals. So with this information, now I present result. And the result is two part. One is steel slag, one is flash. So I present the steel slag first. So for this raw steel slag, so basically this is just the original steel slags, and we testing their leaching concentrations using these 4 methods. So we also in the table we also put the US EPA standard. The DEQ is a local Department Environmental Quality. You know, all the recycling activity, and each state has to be regulated by local DEQ. So that's so we also need to focus on the local DEQ standards. And we also put MCL is for the drinking water, maximum contaminant level in the drinking water standard. So that's just give you roughly idea and say, this is the steel slag we're using. What kind of metal in there? So we can say here is, because this table has many data. So basically the information we want to put out from here is, this is the metal contents have, this is the kind of in terms of content, the ions, the most in there is the cadmium is the less here. Even we have some, no, this is this cadmium is here. So this one I guess I have a typo here. It should be no dichromine arsenics. So this is it's just say TCLP. They don't even didn't testing that. Cannot detect below detection limits. Now, the first thing I want to look at is the pH. So the pH here is we can look at this. If a pH of solid waste, if they are higher than 12.5 or lower than 2.0, so will be classified as hazardous waste. So that way we want to look at pH. So the pH original, the raw steel slag is 10, around 10. So we use MICP, we treat this is the steel slag. Remember, we put a different percentage of the steel slags, and we want to look what the pH of this MICP treat, because MICP treat steel slag, they will be form a cylinder shape. The cylinder shape is we run compression testing first. We go get there how strength increasing. That's the first thing we got. And once we break down the sample, because when you run unconfined compression testing, you break the sample. So we'll break the sample, we can measurement the pH. Then we also can put a part of this break sample through to the TCLP, SPLP, and water leaching test. We also can look their pH, how the pH changed. So in terms of that, so basically in the leaching pH on the right-hand side of this figure, you can see here is this, because this leaching pH is can influence the leaching behavior of the metal. So we really need to know what kind of pH will be. So when we look the leaching pH, we can see here is, you see, in these figures, the leaching pH is basically is increased with the steel slag percentage. When they about like reach the 30%, so 30%, and then they kind of start live off. So that's the final pH for the TCLP reached 7. But remember the TCLP, we put extraction fluid is 2.88. So originally you put 2.88, but once you, after leaching testing, you reach the 7, about 7. So, but for SPLP and water leaching testing, when the final pH reach about like 9.6, so we can see compared to their original extraction fluid pH, so is the pH increasing is indicate here it has a strong acid neutralizations, and they have ability to resist acid corrosions for the MICP treat steel slag products. So that's one thing, because later when we do we will looking the metals, we want to see what kind of the relationship between the leaching. So this figure we're showing is currently we just 6 type of the metal we select here to show you is borons, coppers, magnesiums, calciums, irons, manganese. So that's one we want to compare with the pH. But when we look, we want to say what kind of relationship between that. So we were using the Pearson coefficient here. So you can look at the table here. Want to correlate this to the pH of the leaching pH, and also this the metals, the select 6 metals. We find out borons and the magnesium has highly we say correlate with the TCLP, SPLP's leach pH. So that's kind of really relate to each other. And but when we say that ions among them, they didn't show any correlations to each other. So let's just give you kind of a data show how they relate to the leaching pH. And if you look back to the data, is look the TCLP, the leaching of the steel slags, we can see here is several metals non-detectable, and but the barium, cadmium, chromium, we measure that, we got that, but they're below the EPA and local DEQ's the regulation. So it's below the regulation. So that's give you kind of the one TCLP result. But we also can look today, this is a TCLP, and also SPLP, the same is we do have the barium, cadmium, chromium meet the regulation requirements. Is water leaching testing also meet. So basically, that's the conclusion is from this part is the leaching concentration of metal in the MICP modify this steel slag, and the mixture is in the limit of regulation. So it's no negative environmental concern. So that's about this study here. And another one we want to look for is this is also looked leachabilities. Leachability basically using the leachable ion divided by the total total metals. So we can see how the leachables and of three metals, just present three metals here, the ions, the magnesium, the calcium. So all this we can see here is the ions literally is the highest. Here is 7.35, and so then the ions, leachable ions, quickly decrease to the close to zero when we have more steel slags. So because in the steel slags, the structurally in the ions is in kind of springle structures, so it's very highly stable and resistant to acid weathings. So it's not easily leaching out. So it's a highly related to the extraction flow pH. So we can see here is most ion will be stabilized in there. So it's less leaching out. The magnesite is highly related to extraction flow here. So we can say is when we have the lower steel slag contents, this is the magnesium in the TCLPs higher than SPLP and water leaching testing solutions. But when you have more, they have less. So the kind of the trend reversed. So as it seems like the magnesium is appear is soluble in acid pH, and but if we look the leachability is only show less than 0.616%. So it's really we can see most magnesium was still in the MICP treat soil sample. So and if we look bars also we can see here the bar can be bound to the this is called calci-silica lattice, and the bound calcium in the steel slag can be released and enhance leachability. So the higher carbon ions is produced by the MICP, they may capture the dissolved barium ion and form the barium carbonates. So that way is less leaching out. So now I finished the steel slags. Now I move to the cold flash. cold flashed, also we testing using this methods to testing what kind of the original metal in there. So that's we want to see what kind of mean component in there, and aluminum, calcium, magnesium, manganese. So this metal in original. But when we looked at, we modified the coal ash with this mixing with bacteria. We can see this is the XRD will show the new carbonates here. You can see this is blue colors to show the new type of the carbonates ions, carbonates mineral forms. And also look the pH. So when we look the pH, we say, oh, that's pH. That is the, say the pH is the on the, we should say the bio-modified flash pH. So about like 9.4, 9.5. When we have the times going on, the pH increasing. So the pH kind of, but when we look the leaching pH, so for the SPLP leaching, so that way we can say that pH is quickly be stabilized about like 8. So that's kind of like acid neutralization potentials to make the pH stabilize that. So for the metal, we looked aluminums, bars, and chromiums. When we looked at with this three type of pH, three type of the coal ash, as long as the reaction time, you can see the almost all three type quickly decrease to close to 0. So this is we find out the mineral forms. For example, bar from bar carbonates, chromium hydroxide. So they form that, and they quickly stabilize these 3 minerals. So that's kind of leaching concentration can be decreased. And the next one is this cadmium, magnesiums, and we want to look at that. And this trend is different. You see here is so this is seems like, oh, this concentration going higher with time. Especially looks let's look the calcium here. See the calcium the concentration increasing with reaction times. So it's because they have a calcium carbonate can precipitate. It seems like it doesn't contribute too much for the reducing the leaching of calcium ions. So that may be related to bioleaching of bacteria. But when we look at the magnesium, is see that that's the leaching concentration is much higher after 3 days compared to the raw flashed. So this is, it seems more metal leaching out for manganese, and also same thing for when the beam is also leaching out. So this is a kind of upside with the 3 aluminum bars and chromiums. That 3 is for the metal leaching less, but this 4 is leaching out. So you can see this is the behavior change after you bio-modify this flashed. So based on this work, so this is some summaries. We can say using the steel slag, if we want to modify with MICP, it reducing the metal leachings. It makes less metal leaching out. Is even the leaching out is still in the limit of regulations. So especially during MICP, the carbonates generate is help the precipitation of the heavy metals. So that's reducing their leachable to the environment. So it's kind of benefit using the MICP to treat steel slag, and they can. I didn't present the mechanical improvements, but actually they do improve the mechanical properties, also reducing the leachability. So that's the benefit of that. And for the fly ash is kind of two sides of the biomodifications. Leaching concentration is reducing for aluminum, barons, chromiums, because that relates several things. One is the leachable pH, one is the carbonate generation and absorption this to the precipitating compounds. And for cadmium, magnesium, manganese, and vanadium, they seems increasing. So their bioleaching induced by these organic products from bacteria and potential the computation of carbonate compound may promote to leaching these four type of metals. But there's another way you can say if they're leaching out, so you can easily to reuse the material because the metal already leaching out. So this presentation is based on the two publications. So I can upload to the to the chart for these two paper. So so that's I got two files can be uploaded. So that way is for anyone want to know more, so you can find.
You can upload, yeah, you can upload in the chat box so that you know, if you have a PDF file, you can upload on chat box, so everybody will have immediate access to it.
Right. So so there's two paper I upload to that. So in case my presentation doesn't cover all the detail, so I upload these two PDF in the chat box. So you can download and have, if you have more questions, more detailed information need to answer, so I can answer that. And again, that's my contact information. So welcome. So everyone want to contact me for the future work. So that's here, and I really want to thanks for the funding agency, because this work is I have to do this MICP from the 2009. So it's that's a long time study, because at the beginning I focused on the long-term performance and the mechanical improvement. This environmental leaching study is just started 2 years ago. So that's kind of all kind of the funding support that. Special thanks to National Science Foundations, the U.S. Department of Transportation, because this material can be used roadway constructions. So that's all my presentation. I want to thank you, and I saw a lot of questions from the chat box. So I don't know, Dr. Ray, I just go one by one to answer that.